Hello again, AP Stats students. This is the second video on chapter 26 and the last video. So 2 videos on chapter 26. And the first one, we're in the chi-square model now. We're dealing with categorical data, which are counts. The data is collected in counts, so little check marks in categories, categorical data. And when we do these categorical data tests, we use the chi-square model, which is skewed to the right. It's skewed to the right. And then we look at the data and we get this chi-squared stat. And the chi-squared stat on your formula sheet is the observed minus the expected squared divided by the expected. And then you sum all those values up. That's the chi-squared stat. And we did this in the last video for our chi-square goodness of fit test. And then you get that chi-squared stat. And you could also just get it on the calculator, right? It's pretty easy to get. And then this is your p-value. It's everything above the chi-squared stat. That tells you if you reject or fail to reject the null. Okay, and remember, if you're doing chi-square CDF, actually putting in the value to get that probability, we do 999 for our upper bound, not 99, because the chi-squared stats are bigger values, so we do 999. Okay, so this is the chi-squared model, the new model, not the normal model, not the T model, the final model, the chi-square model that we use for this categorical data. And last class, last video, we did the chi-square goodness of fit test. So watch that video, read the book chapter. And then for this video, we're doing 2 more tests. We're doing the chi-square test for independence and the chi-square test for homogeneity. And those are also both from chapter 26. And the calculator command is just going to be chi-square test for both of these. Chi-square test. Okay, so read my handwriting there. So this was my first video, chi-square goodness of fit test. We did that already. Go watch that video if you haven't yet. And then this video, we're doing the chi-square test for independence, also from chapter 26, chi-square test in the calculator, and the chi-square test for homogeneity. The last thing from chapter 26, also chi-square test on your calculator. And the nice thing about the independence and the homogeneity test is that they function exactly the same way on the calculator. The only difference between them are the hypotheses and kind of what they're looking for. But in order to get the p-value, get the chi-square stat, find the degrees of freedom, it's exactly the same for the independence and homogeneity test. So that's why we group them together. They function the same way. Okay, well, let's just go right to the 2 questions I posted, the 2 free response questions in our Google Classroom, and then just kind of work through an independence one and a homogeneity one, and that'll be that. Okay, now first up, how do you know if it's not a chi-square goodness of fit? How do you know if it's a chi-square homogeneity or independence test? And the nice, easy way to kind of see which test it is if the data is in a 2-way table. So if you got like a table like this is going to be one of the problems we work through. Kind of wrote that out. See how the data is in a table, like a 2-way table, like a matrix, right? When we did a chi-square goodness of fit test, we just had the observed, right? The observed values. We had 22 moose in habitat 1, 31 moose in habitat 2, 55 in habitat 3. Just one row observed values, right? And then we crunched out the expected. But you just have like a row of observed. It was not a 2-way table. It was not a matrix. But if your data comes in a 2-way table and has 2 variables, a 2-way table like this, like a 3x3 or a 3x4 or a 2x3, then you know it's a chi-square test for independence or homogeneity. If it comes in a table, okay. Okay, so let's do the first one. All right, from 2013, we've got behavior risk factor surveillance system blah, blah, blah. Ongoing health survey system tracks health conditions and risk behaviors. In one of their studies, a random sample of 8,866 adults answered the question, do you consume 5 or more servings of fruits and vegetables per day? Okay. Do you consume 5 or more? And the data is summarized below. And you can see, 18 to 34 said yes, but more said no. 741 said no. Only 231 said yes. And then, and then you have 35 to 54. 55 in order. 1291 said yes, and 3,692 said no. So more said no again. And then it says, do the data provide convincing evidence that there is an association between age group and whether or not a person consumes 5 or more servings of fruits and vegetables a day? Is there an association between one variable, age group, how old you are, and the other variable, do you consume more than 5 fruits and vegetables a day? Okay, is there an association? Meaning, is how old you are, does that affect the probability that you eat more than 5 or more servings of fruits and vegetables a day? Are you more healthy as you get older? Does age group affect that probability? And if it does, then you say that there is an association. Or you could say that the age group and then if you eat more 5 or more servings a day, then you would say that they are not independent if there is an association, if they affect each other. Okay, so right away when it says, is there an association, that's your clue that this is going to be a chi-square test for independence. A chi-square test for independence. How are you going to know that? Well, it's going to say, are these two things independent? Or is it going to say, is there an association between these two things? So let's review this. If they are independent, they do not affect each other, then there is no association. So independent equals no association. Not independent, they do affect each other. Not independent equals there is an association. So it's good to have that in your head. Not independent, there is an association. Independent, there's not an association. Okay, and so what is the null? Always. And the null is that there is no association. No association. Just like there is no difference. No association. It doesn't matter what age group you are. It's all the same whether you consume 5 or more vegetables a day. And that's always going to be your null, that there is no association. So let's write that down. So the null is that there is no association between age group and whether or not a person consumes 5 or more fruits and vegetables a day. And then the alternative is that there is an association between age group and whether or not a person consumes 5 or more fruits or vegetables a day. And then you would write that all out. And you just use like their language there. So the null, no association. They are independent. The alternative, there is an association. They are not independent. Okay. And let's just look at this data here. Like how much bigger is 231 than 741? For 18 and 34, 741 divided by 231. So 3.2 times bigger. 741 said no to 231 yes. But then if you look at like the 55 and older, 3692 divided by 1291 is a 2.85. So I don't know. It does look like there were more no's than yeses for 18 to 34 compared to 55. More people said no proportionally. But is that just due to sampling variability? Is the difference big enough to say that there is an association that not as many 18 to 34-year-olds eat 5 or more servings a day, right? And that's what we're going to find out. Okay, so then we check our conditions. One, was it a random sample? And I do believe the problem said that, so check. Okay, 2, the expected cell frequency. Okay, let's come back to this one again. Is there 5 or more in each expected cell? Well, we got to figure that out. We got to find the expected cells. What are these expected cells going to be? Okay. Now, in order to get that, remember when we talked about like independence, basically the percent that said yes or no should be this, like, you know, the same across all of these, right? So what is the percent for the population that um, said yes, we'll do yes. That said yes, I eat 5 or more servings a day. So let's just look at the whole population. 2191 over 8866, which is 24.7%. Okay, so I just did 2191 over 8866.247. So that value right there, 24.7% of everyone said they eat more than five or more servings. Now, if there was no association, then all these age groups should also be 24.7%, right? One individual age group should not be different than the population, right? That's the probability of B given A equals the probability of B, independent. The probability that you eat 5 or more, given you're 18 to 34, is just the same as the probability you eat 5 or more for everyone, for the whole population. So that for your expecteds, you're going to times this 972 total by that 0.247 for that yes. So if the 972 18 to 34-year-olds, what's 24.7, 0.247 of that? And that's 240.084. 240.084. Okay, so I just did 972 times 0.247 is, we would expect 240. We got 231. That's pretty close. So this is the observed 231, and this is the expected 240. And you could do that for each thing. Okay, that's, and another way to get to that expected value, it is or just the same way, but in a formula form, is the row total times the column total divided by the grand total. And that's just what we did. So to get to this 240, the expected value for this cell, for yes, for 18 to 34-year-olds, you could do the row total, 972, divided by the column total, or excuse me, times the column total. So 972 times 2191, get that product, divide it by 8866. That'll get you to that 240 also. Okay. All right. But guess what? We can do that. We could find all those expecteds. Then what do we have to do? Well, then we have to do the observed minus the expected squared divided by the expected for that one. The chi-square formula. The observed minus the expected squared divided by the expected for that one. And do it 6 times. Add up those 6 numbers. That's the chi-squared stat. But guess what? We're going to do it on the calculator. Okay. I'm just explaining how to get those expected values. All right. And they have to be greater than 5 or greater than or equal to 5. Okay, but here's how you're actually going to do it, though. I'm talking you through the method, right? But we're just going to do it on the calculator. Okay, so here's how we do a chi-square test for independence or homogeneity on the calculator. Okay, we're going to enter our data, our observed data, the 231, 741, 669, 2242. We're going to put that in a matrix. So you go to the second x to the negative 1. See that matrix in blue? So second x to the negative 1, second matrix. There they are. And then go over to edit, matrix A, enter. Okay, and then looks like we're working with a 3 rows by 2 columns here. So 3 by 2. So type in the top 3 by 2 matrix and then put in all of your data, your observed data. So the 231, the 741, 669, and so on. All right, there we go. That's the observed. That's all the yes and no's for all the age groups. Okay, great. So you got it all in the matrix. You can exit out now. So second mode, quit. Okay, here we go. Here's how we do it. We go to stat, over to test, and go all the way where we had the chi-square GOF test. This is not goodness of fit. This is an independence one. So we're just doing plain old chi-squared test there. Chi-squared test. This is in a stat test menu. All right. My observed is in matrix A. Now the expected. We didn't put the expected in matrix B, but it's going to throw all of the expecteds in matrix B for us. Okay. So we just have the observed in matrix A, and then we're telling it to throw the expecteds in matrix B. Go. Boom. All right, so this is everything you have to give them. You have to give them the chi-squared stat, the p-value, the degrees of freedom. So the chi-squared stat is 8.9835. P-value 0.0112. Degrees of freedom 2. Okay, how did they come up with that? That's different than goodness of fit. Degrees of freedom for goodness of fit test is categories minus 1. The degrees of freedom for these independence homogeneity tests is rows minus 1 times columns minus 1. And these are always really important on the AP test, all these degrees of freedom formulas. So again, goodness of fit, degrees of freedom is categories minus 1. We did that last video. These matrix ones, the two-way table, homogeneity, independence ones, is rows minus 1, 3 rows. So 3 minus 1 times columns minus 1, 2 columns of data, so 2 minus 1. So 3 minus 1 is 2, 2 minus 1 is 1, and 2 times 1 is 2. So we are using the chi-square model with 2 degrees of freedom. And your calculator does give that to you, okay? And just remember how to do this on the calculator. If you were doing it like, you know, more step-by-step. To get that p-value, you go second distribution menu. So not normal CDF, not TCDF, chi-square CDF. And then you would put in your chi-square stat, which was 8.9835. 999 upper bound, 2 degrees of freedom. That gives you your p-value. You don't have to, our calculator already did this for us, but it's 0.0112, great. And that's what we got, 0.0112, okay? So again, calculator really does pretty much everything for us, doesn't it? Okay, now before we state our conclusion, let's finish up our conditions. So for the expected cell frequency, they all have to be greater than 5, and we have to show that all those expected cells are greater than 5. Our calculator put the expected cells in matrix B. So let's get those. So go to second matrix, and see how my matrix B now has a 3x2 in it. So go over to edit, down to matrix B, enter, boom. Okay, now quick jot those down. And you had to show it. So in the AP test, we would quick jot these down. We would expect 240.2, it was 231. 731.8, it was 741 actually. So these actually look pretty close. 719.38, although that's different. Well, 2191.6, 1231.4, and 3751.6. Okay, they are all greater than 5, so check. All expected cells are greater than 5. Finally, the counted data condition. Counted data, is the data categorical? And I would say yes, counted data condition. The data are counts in categories by age group and whether or not they ate 5 or more servings of vegetables a day. Check, just give the categories. Okay, so it was, the problem state sample is random. Check, they're more than 5 in each expected cell. Check, the data are counts in categories by age group and whether or not they ate more than 5 vegetables a day. Check, check, all conditions met. All right, let's do it. P-value, 0.01. So how about we use a 0.05 alpha? If we used a 0.01 alpha, we would fail to reject, right? But if we use a 0.05 alpha, which I'll do, using alpha equals 0.05 with a p-value so low, we reject the null. There is sufficient evidence of an association between age group and whether or not a person consumes 5 or more servings of fruits and vegetables per day. So again, with the p-value so low, using alpha equals 0.05, with the p-value so low, we reject the null. There is sufficient evidence of an association between age group and whether or not a person consumes 5 or more servings of fruits and vegetables a day. So we weren't quite close enough. The observed was not quite close enough to the expected. Although if we would have used alpha as 0.01, it would have been close enough. Okay, great. So that's your chi-square test for independence. A lot going on there. What might you run into? The degrees of freedom formula, rows -1, columns -1. Remember, the null is always no association, or it might say they are independent, right? And the alternative is always that there is an association. They are not independent, is how they might see that. Put it in a matrix, chi-square test on your calculator, bam, there you go. Remember, how do you get the expecteds for each of these? Row total times column total divided by grand total will get you that. Okay, now let's do a chi-square test for homogeneity, which functions the exact same way. The only difference is how you write the hypotheses. So the next problem, manufacturing plant, recreational vehicles, they get parts from 3 vendors. And then we're having defective issues. And the manager wonders if all the vendors might be contributing equally to the defect issue. So are some suppliers, do some suppliers have more defective parts than others, right? Or is it all just, all the defective parts are pretty much the same for all suppliers? The rate of defection is the same or not? And you can see that homogeneity means the same, right? Homogeneous is the same. Okay, so how do you know if it's an independence or homogeneity test? The independence will say, the question will be, are these 2 variables independent? Or it'll say, is there an association between blank and blank? Then you know it's an independence test. Homogeneity will ask, is the distribution of this variable the same for these things? And for this question, it says, the plant manager wonders if all the vendors might be contributing equally, the same to the defect issue. So that contributing equally, and the fact that it's in a matrix, right away, it's independence or homogeneity, because it's a table, a 3x3 table. And then when it says contributing equally, he wonders if it's contributing equally, then it's a chi-square test for homogeneity. And we'll run through this one kind of fast. So the null is always that what? It's always that they are the same. They're the same. Okay, just like in independence, it was that they are independent. And then for homogeneity, it's that they are spread out equally. It is the same. So for the null, I'm going to say the vendors are contributing equally to the defect issue. I'm just stealing their language. The vendors are contributing equally to the defect issue, and the alternative is that the vendors are not contributing ... equally to the defect issue. Okay, so that's your null, that's your alternative. Let's just do it in the calculator. Oh, sorry, it's my phone. We'll get that later. Okay, let's just quick do it on the calculator, and then we need the expected cells for the expected cell frequency condition. Got to be 5 or more. So we got to do it on the calculator first anyways. Okay, so I'm going to my matrix, and it looks like this time, second x to the -1 matrix. This time, it's not a 3x2, it's a 3x3. And then just put in the values just how they look, the 53, the 48. You'll be doing this in your homework, I imagine, entering numbers into a matrix, if it's a homogeneity or independence one. Okay, good. Got my values in a matrix right there. And then we're just going to go to chi-square test. Stat over to test, chi-square test. Observed, expected, there we go. Boom. Okay, so let's write down the chi-squared stat. It's 7.401. The p-value, 0.116. Degrees of freedom, 4. Rows minus 1 times columns minus 1. 3 minus 1 times 3 minus 1. 2 times 2, 4. Boom. There we go. That's all you need to do. These are actually really easy. You just put them in a matrix, and then it'll give you your chi-square set, your p-value, your degrees of freedom. We can check the conditions now, because those expected cells are in matrix B. First, was it a random sample? Let me look at the problem. The manager wonders, the plant manager reviews a sample of quality assurance inspections from the last 6 months. Okay, so he said he reviews a sample of quality assurance inspections. Were they randomly sampled, the quality assurance inspections? I might put a question mark there. It doesn't actually say the word random. Okay, expected cell frequency next. This is a sample size condition. We gotta give them those values, give them the matrix. So go to second matrix again, go over to edit matrix B. Boom, there they are. And you gotta jot them all down in a matrix. And I just do like 1 decimal. So, you know, really quick, 57.7, 51.5. And this is better than doing these by hand, right? But we could do them by hand. We talked about that, how to get all these expected values by hand on the last problem. And sometimes you have to do that. Remember, it's row total times column total divided by grand total will get you these expected values. Okay, and they are all greater than or equal to 5. Yes, check. So all expected cells are greater than or equal to 5. Check. Counted data condition. Counted data, is the data categorical? Counted data condition. And you would say check, and you would say the data are counts in categories by vendor and by number of defective parts, is what I would say. Counted data, check. The data are counts in categories by vendor and condition, you could say, the condition of the parts. Right, you know, so you say other than random, might not, all conditions met. Check, 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 great. Okay, finish it up. What are we going to say? P-value 0.116, using alpha equals 0.05 with a p-value so high, we fail to reject the null. There is not sufficient evidence that the vendors are not contributing equally to the defect issue. So kind of a double negative there, but that's fine. With a p-value so high, we fail to reject the null. There is not sufficient evidence for the alternative. There is not sufficient evidence that the vendors are not contributing equally to the defect problem. So we can't conclude that one vendor is worse than the other, according to this test. And that's it. That's the chi-square chapter 26 stuff, everyone. Okay, good job. Again, read the chapter is helpful. As you work through your homework, you know, just how to do a test, the degrees of freedom formulas, how to get the expected values. You guys should be good. And then I'll take any, if you guys have any questions on any of these Albert problems, we can do those during our Google Meets too. Okay, great. So you have everything you need on chapter 26, and then I'm planning on making the chapter 27 homework and test and video tonight. That's my plan. We'll see if it happens, but I think it will. All right, thanks guys.